Kia ora and welcome to video 9 in the series Delightful Differentiation. This video is going to be run through by a former student of mine, Oliver. Oliver was with us at MAGS for 5 years. I had the pleasure of teaching him or knowing him for 3. He achieved scholarship 3 years in a row in calculus, and in his final year at high school, it was really a pinnacle achievement for him. 8 scholarships in the NZQA exams. And it was testament not only to his intellect, but his extreme hard work. And I've said that about a lot of the students through these videos. You know, the students who achieve scholarship, it's not just the intellect, insight, and whatnot, it's also hard work. And for Oliver, Oliver had a little book of notes, I say pearls of wisdom. Every time I said something in class, he would write it down. And then if he didn't understand what I had said in class, he would bring up his little notebook and cross it off and ask me for the extra details. So he did the right things to achieve those results, and he's going to continue to succeed in the future at university, I'm sure. So the problem that Oliver's going to cover with you today is an optimization question. We've got a shaded area there, 2 segments on the outside of the circle, and then a segment in the inside of the circle. So you need to work out where that horizontal line should be so that the shaded area there is minimized. All the best, and we'll catch you in the next one.
Alright, let's get started. So first off, we want to find the value of h that gives us the minimum shaded area. So first we need to find an expression for the shaded area and differentiate that, set the first derivative to 0, and then find the h value that makes the first derivative 0. Cool. Alright, let's get started. So first off, find an expression for the area, or more accurately, the shaded area. Area equals z plus 2c, right? Z is the shaded area at the top there, and C is the shaded area at the side. Now, we don't actually have formulas to express these irregular shapes as areas, but what we can do is write them as as the difference between 2 known shapes. So what we can do is we can write area of Z equals area of semicircle minus the white area, and the area of 2C equals the area of the rectangle minus the white area. So we can do that. But what is the white area? Well, looking at that, I can think of a way to split it up. So split up the white area into these sections, into 2 right angle triangles and 2 sectors. And because we know the formula for the area of a triangle and the area of a sector, we can express the white area pretty easily. So, this is what I've just described. We've substituted Z with the area of the semicircle minus the white area, and this area of 2C is instead substituted with the area of the rectangle minus the white area. And that's just expanded. We know that area of a semicircle is half pi r squared. Area of a rectangle is base times height. Area of a triangle is half base times height. And area of a sector is theta times r squared. Just more algebra cleanup. And we have the expression here. So, our expression, shaded area equals half pi plus 2h minus 2 base times height minus 2a. That has too many variables. We don't want that. Because when we differentiate the expression, we want it in terms of just one variable only. So, what can we do? Well, first off, we need to find the relationship between all these variables. And how convenient, we have a right angle triangle that we can use. Cos A equals B over hypotenuse, but because hypotenuse is 1, cos A just equals B. Likewise, sin A just equals H because hypotenuse equals 1. So, we want to differentiate the shaded area, but with respect to what? Well, if you think about it, despite the question asking us to find the value of h that enables the minimum shaded area, we don't actually want h to be in our expression to differentiate. Why? Well, if we want everything to be in terms of h, we'll need to convert the a into h. But that's a bit awkward because we have to write inverse sine of h equals a and substitute that, right? The problem with that is, how are you going to differentiate the inverse sine of h? There probably is a way to do that, but we don't need to go down that road, and there's a much easier path. Instead, we substitute everything and rewrite everything in terms of a, the angle. That's what we're going to do. And differentiate the shaded area in terms of a, the angle. A bit of product rule here and there, and we'll get this expression. Set the derivative to 0. Simplify it. Do a bit of algebra. Use a bit of identities, because we don't want cos a and also a. We can deal with cos squared a because we can always just factorize whether it's by quadratic or common factor and solve it that way. But when you have both cos a and sin a, it gets a bit messy and awkward. So converting everything to cos 2a and then using your identities again to convert it into an expression with cos squared a, simplifying it more, factoring out the cos a. And so we're left with two possibilities, either cos a equals 0 or cos a equals half. So we'll look at where that takes us. That means either a equals pi over 2 or a equals pi over 3. While we know one of them will probably be the minimum area and one of them will be the maximum, we could use second derivative to find the answer to that, but this question doesn't ask us to do so, and there's a much easier way. All we do now is substitute this into the original shaded area expression. Oh yeah, and here we know that if a equals pi over 2, h equals 1. If a equals pi over 3, we know from your special triangles, h equals root 3 over 2 units. So this is just substituting the different values of h and a into the original expression. We see here when h equals 1, the shaded area is about 0.43, whereas when h equals square root of 3 all over 2, the area is much less. Therefore, we know that when h equals square root of 3 over 2 units, the area is a minimum.